Okay, so today we would like to talk about the theory of diffusion of colloidal suspensions, and this is a pretty actually useful part of the lecture, that a technique called dynamic light scattering actually utilizes this theory to measure the hydrodynamic particle size or hydrodynamic size of particles in colloidal suspensions. So let's get into the context here. So let's say we have these dilute particles A, suspended in a stationary liquid B. And the assumption here is that the particle size of the particles are fairly small, but are still considerably larger than the site of the solute molecules. So let's put a note there. So let's say solute molecules. Okay. And, from what happens here is that there's going to be collisions between these particles with the molecules of the liquid, which will result in an erratic motion of spheres, and which is generally known as the Brownian motion. Okay, so in the following, we would utilize Einstein's theory or Einstein's derivation to show you how we get to the diffusivity or the diffusion coefficient of the particles suspended in the liquid. So let's draw a simple idea of a Brownian motion. So it's going to be an irregular motion here, right? So it's going to be like, some random collisions of the solute molecules with the sphere, or the sphere with the solute molecules, right? But if we take a look at a infinitesimal or infinite small, volume here, let's say we take a look at this really small space here. Okay, and if we zoom in, we would view that inside this box, let's say that the particle is experiencing a force causing it to move in a positive x direction. Okay, so let's say this is the x direction, and there's going to be a force exerting on this. Okay, so basically, if we put this into context, that means that this force, this, irregular oscillating force F is causing the particle to have its random motion. Okay, so we'll say F exerted on the particle causes the random motion of particles. Okay, and here are some basic assumptions of the force F. Okay, so the first one is that this oscillating force is only dependent on position but not time. So F is only F of x, not F of t. So it's not a function of time. And the second one is that F is only in the direction of the x-axis, or we define it such that F is in the direction of the x-axis Okay. Now, so we know that there would be a irregular motion of a single particle, but if you look at the whole suspension as a whole, there's actually no net movement or net motion. What does that mean is that the system is now under a dynamic equilibrium. So individual particles are undergoing their random motion, but collectively, the particles collectively are not, having any motion. They would cancel out, okay? So that's the concept of dynamic equilibrium. So now let's look at the whole colloidal suspension as a whole. So let's, draw a spacer here. So there's a spacer. And let's take a look at the, draw a control volume that has a lot of particles in it, okay? So now let's draw a control volume. Let's say we have a cubic control volume. And within that control volume, we have this many numbers of particles. And we'll say that we have, we have nu as the number of particles per unit volume. Okay, and we say that under the condition of dynamic equilibrium, so under the condition of dynamic equilibrium, as I mentioned, that means that if we look at all the particles, the net motion and the net displacement should be 0. Okay, and that means that the number of particles as a function of position. So we'll say that nu of x, which is function of position, is such that the free energy, which we use delta G, vanishes for an arbitrary displacement. So this is basically another way of saying that the energy is conserved in this system, right? So if you look at the individual particles, the energy is not conserved, but if you look at all the particles together, the energy should be conserved, and delta G should be 0. Okay? So it's going to be vanishing for an arbitrary displacement. We'll call that delta X. If you put that into an equation, that means delta G would equal to 0 equals to delta H minus T delta S, right? So this is the definition of delta G. Okay, so now how do we know what is delta H and what is delta S, right? So again, let's look at our control volume, okay? So, and the definition of delta H. Remember that by thermodynamics, we know that delta H equals to, I think it equals the internal energy plus PV. So let's put it another way. So H equals to U plus PV. And in this particular system, delta H, because the internal energy is not changing, because internal energy is only a function of temperature, so delta H only equals to P delta V. Okay. And P delta V, if we continue the analysis here, P delta V is equal to what? Equal to the force exerted on a particle over the area. So F over A, or F delta V over A, and unit-wise equals to F times the displacement X. Okay. And so let's assume that, the control volume here, we have a control volume like this. And we define X equals to 0 here and X equals to L. And this would be our unit area. So basically delta H here would be the collective work. So the collective work exerted on all particles, when they're traveling from X equals to 0 to X equals to L. Okay. So this equals to, a second, sorry. Okay, so delta H here equals to the integration, the negative integration from 0 to L times the force F exerted on individual particles times the number density of particles per unit volume times the displacement dx. Now let's take a look at how we define thermodynamically from a statistical thermodynamic point of view, how we take a look at the delta S term. Okay. So basically, if you look at the Boltzmann entropy formula, let's introduce that. So Boltzmann's entropy formula. Which states that the entropy from a statistical mechanic point of view equals to the Boltzmann constant, K sub B, times the natural log of omega. What's the omega? The omega here is the number of possible microstates. Okay, so based on that definition here, the delta S can be written as the following. So delta S here equals to the Boltzmann constants times the integral from 0 to L partial nu partial x delta x dx. Okay, and basically this is the later part here can be understood as the number of possible states of eta in the delta x in the displacement. Okay, so if you plug these back into, so let's call, this is equation 1, this is equation 2, and this is equation 3. So now let's combine equation 1, 2, 3. So combine equation 1, 2, 3, we will see the following. We would see that delta H minus T delta S equals to 0. Delta H equals to the negative integral from 0 to L, the force exerted on a single particle times the density or the number density of the particles times the delta x dx plus the integral of the Boltzmann constant times partial nu partial x times delta x dx equals to 0. And so that gives us to our first important conclusion, which is that the force exerted on individual particles times the number density of the particles, so it's like the collective force acting on all particles, equals to the Boltzmann constant times absolute temperature times the number density or the number of possible states of the particle density within that control volume, right? So this is our first important conclusion here. And let's call this equation 4. Equation 4 is important because we'll use this result to actually get to the diffusion coefficient of the suspended particles. Okay. So the first key concept here, let's kind of review this again, is that, each individual particle is undergoing Brownian motion. So it's going to be a regular erratic motion. But if you look at the suspension as a whole, it's not really moving, right? There's nothing happening. That means the energy must be conserved. Okay, so using the thermodynamics here, if energy is conserved, that means delta G equals 0. So that means delta H minus T delta S is 0. The delta H here is going to be the collective work exerted on all particles collectively together. And the T delta S is basically using the idea of the Boltzmann entropy formula, meaning that the entropy here is equal to the Boltzmann constant times the possible microstates within the system. Okay, so using these two together, we finally get to equation 4 here that has this expression of the force times the nu equals to the Boltzmann constant times temperature times partial nu partial x. Now, to continue our discussion, we come back to the idea again of the dynamic equilibrium, right? So again, or let's write the under better, looks like a V. Under dynamic equilibrium, the collective movement of particles by the force F and diffusion process should equal to 0. So putting it into a better context is, under dynamic equilibrium, the collective motion or displacement of the particles should be 0, or the net displacement should be 0. So that means that the movement of particles exerted by the force F plus the diffusion process together should equal to 0. So the collective movement of particles by the force F and diffusion process should equal to 0. Okay. So let's call the first one here is A and diffusion as B. So let's take a look at the movement of particles due to the exerted force F. So first let's look at the velocity of a single particle. The velocity of the single particle, based on Stokes Law, so based on Stokes Law, the velocity equals to the force exerted on a single particle, and because it's moving through the liquid B here, it's going to, experience drag, right? So it's going to, the velocity equals to the force divided by the drag coefficient, or equals to F divided by the drag coefficient. And for a spherical particle, that equals to F over 6 pi viscosity times the radius of the particle A. And now we can also conclude that the collective movement of all the particles, meaning this is a flux. The collective movement, or the flux, are equals to eta times F over the drag coefficient. The drag coefficient equals to F times nu over 6 pi mu RA. So let's call this equation, I think it's going to be equation 5 now, right? Yeah, equation 5. Now let's look at the diffusion, right? So the diffusion process from Fick's law we know that the flux equals to the negative of the diffusion coefficient times the flux of the particles, so the change in the number of particles over x. And that's called equation 6. So from equation 5 and 6, we know that the net movement should be 0. So 6 pi mu RA minus diffusion coefficient times partial nu partial x equals to 0. Okay? And remember, from equation, I think it's equation 4, right? So from equation 4, the product between the force and the number density equals to what? Equals to the Boltzmann constant times temperature times partial nu partial x. So that gives us the following. That gives us that the Boltzmann constant times the absolute temperature over 6 pi mu RA partial nu partial x equals to the diffusion coefficient times partial nu partial x. Now these two terms can cancel out, and finally, we see that the diffusion coefficient here equals to equals to the Boltzmann constant times temperature over 6 pi mu Ra. Okay, so basically you can see that the diffusion of suspended particles, that diffusion coefficient here is proportional to temperature, but inversely proportional to the viscosity of the stationary liquid, and inversely proportional to the size of the particle. So the larger the particle size, the smaller the diffusion coefficient.